Of course, we can do the realization using MATLAB. You can use SS to get the system G, okay, state model. Um, we can do the canonical realization, especially control canonical realization, using canon of G with this option, the companion. Okay, if you run this, then you will get the control canonical form, where the G could be transfer function, but here is given as the state model. So the state model is not in canonical form in general. So when this G not in canonical form is given for the input of this canon, then you are going to get this control canonical form. But also, the MATLAB offers the realization called the modal form. So what is modal form? If you do this canon of G, okay, without any option, then actually, in fact, you get the modal form. So what is modal form? Um, we may get some problem when the eigenvalues of A become the complex. Like, suppose you have 4 eigenvalues, and 2 of these eigenvalues are real, but 2 of these are complex, like alpha plus j beta, alpha minus j beta. Note that these two eigenvalues, complex eigenvalues, come as pair, right? They should be complex conjugate of each other. Okay, so suppose you have the two eigenvalues complex, but in that case, if you do this Jordan decomposition, then you are going to get lambda 1, lambda 2, and these two complex eigenvalues. But in that case, if you do the Jordan decomposition, the realization, then you are going to have complex entries in your A matrix. Okay, then the realization will contain these complex numbers, and these complex numbers may not be used for practical applications. So we need real numbers to implement the state model in practice. So we want to avoid complex numbers, okay, in our ABC matrices. I mean, that's what is needed in practice. So in that case, we may not have this complete the Jordan canonical realization, and we have to take a little bit of detour to solve these issues. How would you get just real numbers instead of complex numbers in the A matrix, or sometimes the B or C matrix? But the problem here normally comes in this A matrix. Okay, so the first thing you can notice is this lambda, yeah, the lambda that is supposed to be a diagonal matrix is T inverse times AT, because A is decomposed as T times lambda T inverse. Okay, so this lambda will be T inverse if you just pre-multiply with T inverse here and post-multiply with T, then you will get this equation. Okay, so then what we are going to do is to multiply certain matrices before and after this lambda, so that the resultant matrix will have all real numbers here. So initially we had lambda 1, lambda 2, and alpha plus j beta and alpha minus j beta. I mean, that was the original lambda. But now we just multiply Q1 and Q, so that the resultant matrix becomes like this. Okay, so this is what we are going to have for new A matrix. Okay, so that's the realization after this the modified Jordan canonical realization. Okay, so that means the T was this one. Okay, but now you just pre-multiply this one with Q inverse and post-multiply with Q, and so it is going to be like this: Q inverse T inverse A TQ. Okay, because we have Q inverse Q. Okay, so this is same as TQ inverse A and TQ, and we call this TQ P. Okay, so this is new transformation matrix. Okay, so that your lambda becomes this one. I mean, this one doesn't contain the complex number anymore. Okay, so you have P inverse AP. Okay, if you have a certain P, well, the P is basically T times Q. And what was T? T was basically a set of eigenvectors. Remember the original Jordan decomposition. Okay, so you use set of eigenvectors to get T. And if you use T and T inverse, okay, then you normally get a diagonal matrix of eigenvalues. If all the eigenvalues are real, then that's fine. But suppose some of eigenvalues are complex, and then we do a little bit of modifications, right? Now we apply the Q here, and Q here. Okay. Okay. So then now you have P and you have the P inverse. Okay. So now you use just different transformation, okay, to get the different lambda. Okay. So now this is like a new lambda you are going to get. Okay. Okay. So what would be the TQ? So T, remember T was the set of all the eigenvectors. So you have T1, T2, T3, T4, but this T3 corresponds to like a lambda 3, and T4 corresponds to lambda 4, but this lambda 4 is complex conjugate of lambda 3. Okay, so it was alpha plus j beta, and this is alpha minus j beta. Okay, so in this case, T4 happens to be complex conjugate of T3. Okay, so these two have the relationship, okay, of complex conjugate. Likewise, the T3 and T4 got the same relationship, the complex conjugate relationship. And so this T matrix will look like T1, T2, T3, and T3 star. Okay? And because these are the complex numbers, the T3 and T3 star will be complex as well. And so if you write T3 as real part of T3 and imaginary part of T3, because this is complex number, so you can split this complex number into real part and imaginary part. And T3 star will be real part negative minus J, the imaginary part. Okay, right. And then how about Q? Well, we haven't clearly, yes, here's a Q actually. So if we use this particular matrix Q and the corresponding Q inverse here, then this lambda will turn into this new lambda here. So the original lambda, remember, was look like lambda 1, lambda 2, and alpha plus j beta and alpha minus j beta. Okay, you had this lambda, but if you apply this q inverse and q to this lambda, and your new version of lambda will look like this. Okay, you can easily check that. Okay, so now you take this q here. Okay, so this is q because you want to see what this p look like. Okay, because we need this p anyway, so that the p lambda p inverse becomes a, right? So now we want to see what p will give you desired realization. Okay, so here's a t and here's a q, and if you just multiply these two, then you are going to see that the t1 t2 becomes exactly t1 t2 because of these first two columns. These two columns do nothing, okay, for this t1 t2. But how about this one? Okay, so because of 0.5 and 0.5, this will give you the sum of these two, okay, with the factor of half. Okay, you just add add this, then that would be 2 times real part of t3 times 0.5, and that will give you real part of t3. And how about this? Okay, so because of this last column here, so these two things will be subtracted from each other with the multiplication of this much, and that will give you imaginary part of t3. Okay, so idea is the following. So from t, you've got t1, t2, t3, and t3 star. Okay, you will get this, and the initial lambda will be lambda 1, lambda 2, lambda 3 star, lambda 3, and lambda 3 star. Okay, so now you have these two complex numbers that we don't like. So we don't want to see complex numbers in A matrix, I mean realized matrix, AJ. And so, okay, so instead of using this T, let me use P instead. That T will be T1, T2, real part of T3. Okay, so because T3 consists of real part and imaginary part, you only take the real part of T3 for the third column of P, and here the last column, that will be imaginary part of T3. Okay, so these are all real numbers. Okay, so if you use this P, then the new lambda, so this was AJ, okay, previously, but new AJ will look like this: lambda 1, lambda 2, alpha, beta, minus beta, alpha. Okay, so all the other entries are 0. Okay, the final topic for this lecture will be the stability for this linear system. Well, we have discussed the stability using these eigenvalues of A matrix. If the eigenvalues of A matrix are all in LHP, we know the system will be asymptotically stable. It means this x, okay, not y, this x goes to 0. I mean, it's quite a strong condition compared to just taking y to 0. Okay, the whole state vector will go to 0 if these eigenvalues of A are all in LHP. And this is called internal stability because normally x is hidden in the input-output relationship. Y is something you see, but x is normally hidden in the block. So you have u and y. and you have this state equation bu, and here is x, and you have cx, y equals cx. And so this x is kind of internal variable that may not be seen 100%. Okay, so but we take this x to 0 if we have eigenvalues of a all in LHP, and so this kind of stability is called internal stability. Now let me introduce another way of checking asymptotic internal stability using so-called positive definite matrix. So what is positive definite matrix? And positive definite matrix P is such that X transpose P times X greater than 0 for all non-zero X. Okay. And normally this P is assumed to be symmetric as well, because X transpose PX is same as X transpose symmetric part of P times X. So we often assume that the P is P transpose, which means P is symmetric. Okay, so what does it mean? Well, every matrix can be written as P plus P transpose divided by 2 plus P minus P transpose divided by 2. So it's the same. I mean, if you just sum these two, then you are going to get P. And this is always symmetric. So this is called the symmetric part of P, and this is skew symmetric part. Okay. The interesting thing is X transpose the skew symmetric part. Okay. This is always 0. Why is that? So P transpose Px minus X transpose P transpose X, right? Why is it 0? Because this is always scalar. This is just number. Okay. This X P is n by n matrix. So, for example, this is 1, 1, 2, 3, and you have X is x1, x2 transpose, and this is x1, x2. Okay. Then it's x1 square, and if you do the multiplications, you will see this is plus x5, x1, x2 plus x2 square. So this is just a number. This is not a vector anymore, just number. So if we take the transpose of this one, then because this is number, the transpose of a number is same as just original number. So x1 square, 5x1, x2, x2 square is the same. Okay. So, but if we do the transformation of this one, okay, suppose you have A, B, C transpose, that's T transpose, B transpose, A transpose. Okay, so order of these matrices will be reversed. Okay, so now you can see that if we do the transformation of this one, okay, X transpose PX. Okay, so X transpose PX transpose. Then what happens? Now this X transpose and this P transpose and X transpose T, so that's X. Okay, so the transpose of this one is exactly this one. But I said, I mean, this is scalar, so transpose of scalar should be just the same scalar. So it should be 0. I mean, these two must be the same quantities. Okay, the scalar of transpose should be the same scalar. Okay, so these are the exactly same thing. Okay, so So X transpose times the skew symmetric part, so this part, skew symmetric part of P times X is always 0. So what is left is only symmetric part. Okay, so uh, so the point is, so X transpose P X is X transpose P symmetric part X plus X transpose P skew symmetric part X. But this is equal to 0 all the time. So that's why we can normally assume that the P is just a symmetric. So this is the positive definite matrix. So if certain matrix is the positive definite, it means X transpose Px is always positive for non-zero X. Okay, so that's the definition of positive definite. So this is example of positive definite matrix when P is 1, 1, 0, 0. Okay, then X transpose P X. So now we have 1, 0, 0, 1, and this X is X1, X2. X transpose means X1, X2. Okay, if we do the multiplication, then it's X1 squared plus X2 squared. And we know this is always positive for all non-zero X. If X1, X2, okay, they are equal to 0, okay, at the same time, then this is going to be 0. But for all the other cases, I mean, this is always positive. So in that case, we call this P matrix positive definite. And now we are going to use this positive definite matrix and now this V function, which is defined as X transpose Px, to check the asymptotic stability of a system. Okay. Here, what is the concept of this V? Well, this is always positive, as I said. I mean, except x equal to 0. So suppose this x-axis is x. I mean, this is not a scalar. It's a vector in general. And now this y-axis is v for this x transpose px. You have certain matrix and x transpose and x multiplied, and then you are going to have certain function like this. Okay. Well, if p is like a scalar, x scalar means going to be is going to be like ax squared. Okay. If p is like just number and x is number, then is x transpose x is x squared, and so this is a parabolic equation. Okay. So this is always positive except x equal to 0. Okay. You can look at this one in 3 dimension. Right? For example, you have 3 dimension like x1, x2. Okay, and you have v here, and you have this parabolic shape drawn in the three dimension. Okay, and then what we are going to see is this condition here. So suppose this v dot is shown to be negative. It means the derivative of v is always negative. So coming back to this, the graph of v. Now for some specific x, okay, we have corresponding v value, and now I mean this v dot is time derivative, is not derivative with respect to x, but at some particular time t, we have a particular x, okay, and for that x we have the v. And suppose this v is decreasing. Okay, so as t goes to infinity, okay, as t gets increased, suppose the x here, x moves this direction. Okay, so that's how x changes over time. Okay, and now the function that we defined, okay, which contains x here, changes this fashion, right? Certain numbers, positive number, that's the initial v. But suppose the value of v gets decreased, or the v dot is negative all the time, it means the v will get decreased. Okay, and eventually this v will go to 0. Okay, v cannot be negative number. Okay, the minimum value of v is equal to 0. Okay, but at v equal to 0, we know x should be 0, right? Because v is always positive for non-zero x. But now you are saying that the v is equal to 0. It means x should be 0 by the definition of positive definite matrix. Okay, so that's the logic. So now we are given this model, okay, linear model. Now we want to see whether x goes to 0. Okay, we want to see this convergence through this v. We are going to call this v Lyapunov candidate function later. But now this is nothing but just the function, but which involves positive definite matrix. Okay, so because p is positive definite, this v is always positive, except for the case where x is equal to 0. Okay, so it looks like this. Okay, over this x space, now you can define this graph of v, and if this v has this property, like over the time, v dot is always negative. If that is true, then the v must go to 0, right? And when v reaches 0, x must be 0 because of the definition of the p, okay, positive definite matrix. Okay, so let's make this concept the more concrete, okay, using these equations here. Now we know v dot less than 0 for all the time. We take v to 0 and x 0. Okay, so that's the logic. So let's look at v dot. What is v dot? Well, v was x transpose px. Okay, and now you take the time derivative of this v. So first time, okay, you differentiate x, and then next time you differentiate this one, and so you have this. But we know x dot is ax plus bu, and here we do not consider u. I mean, this is equal to 0 for checking the stability for the moment. I mean, when we look at the stability of a linear system, we normally assume that the u is equal to 0. There is no external input. Okay, if that is the case, then this x dot, this ax, okay, you just plug in ax here, okay, and here, okay, then now you have to take the transpose. So x dot transpose would be a transpose a transpose. Okay, so that will be a x transpose a transpose, and this one a transpose. This one is simply ax. Ax. Okay, right. Then you can write this expression as this one here, and you have x transpose in front and x at the back, and in the middle you have this matrix a transpose p plus pa. Okay. Now, what we want is to have this, okay, have this quantity to be less than 0 all the time. Okay, that's what we want. Okay, so if this is true, then we can say v goes to 0 and x goes to 0. Okay. But when would you achieve this inequality? Well, let me introduce another positive definite matrix. So Q is another positive definite matrix. So in that case, we simply call Q greater than 0. It doesn't mean that each entry of Q is positive. It means Q is positive definite. Remember, X transpose Q X is positive for all non-zero X. And that's the definition of this equality being applied to a matrix. Okay, so now this Q is positive definite. What we want is to have this guy less than 0 all the time. So that means the matrix in the middle is now set to minus Q. Okay? Minus Q. So this is minus Q. So it means you have minus X transpose QX. Okay? And we want this guy to be less than 0. Yeah, of course. I mean, that will be true because Q is positive definite. So this part is always positive. We have negative sign. So it should be less than 0. Okay. So if this is true, okay, so A transpose P plus PA equal to minus Q, where P and Q are positive definite. If this equation is satisfied, okay, if this equation is satisfied, then this will be X transpose QX with negative sign, and this is always negative. So V dot will be negative, and so V goes to 0 and X goes to 0. Okay, so this is a critical condition for a given system to be asymptotically internally stable. In fact, this equation is called Lyapunov equality. Okay, that's why this one is called Lyapunov candidate function later. But this is called Lyapunov inequality. This is a matrix equation. Okay, A, P, Q, they are all matrices. Okay, so given A, so A given, so x dot equals AX, so this A given A, now we want to check the stability, internal stability of A using Lyapunov function, candidate function B, okay, with certain P. I mean, you have to choose this P. So P must be chosen in some way so that the V dot is shown to be negative. So you have to choose this. Okay, you have to choose this and you show that. Then we know V goes to 0 and X goes to 0. Okay. So how would you choose this P? I mean, that's something that we have to do. Okay. So now this example gives you some idea that not every P will show you this, even though this A is okay. Like eigenvalues of A are all in LHP, and we know this guy will be internally stable. We know that. But if you choose P wrongly, then you may not show that the V dot is less than 0. So you have to choose a right P so that the V dot is shown to be negative for this internally stable system. Okay, so suppose the A is given like this. This is stable. I mean, this is asymptotically stable because all the eigenvalues are in LHP. In fact, these are eigenvalues. Okay, so it's a stable, But if we choose P like this, so P is simply identity matrix, then you can check that the A transpose P plus PA will be this one, and this is not positive, this is not minus Q. You can check X transpose, now this matrix here, minus 1, 10, 10, minus 1. So you have x1, x2, here x1, x2. Okay, if you just do this multiplication, then it's going to be this. Okay, and this is not sorry, I think we want to check this. Okay, we want this guy to be negative definite. Okay, for non-zero x. Okay, for whatever x, so this one should be negative. Okay, but if we choose x1 equal to 1 and x2 equal to, say, 0, okay, 1 was 1, then what happens? Then this one gives you minus 1 and plus 20, and this one minus 1 is 18. Okay, so 18 is definitely greater than 0, and so this is not less than 0 all the times. Okay, so it means this is not negative definite. Okay, so if we use this P, then you may not show that the V dot negative, even though this A is internally stable. I mean, if even though the eigenvalues of A are all in LHP, you may reach the conclusion. Okay, so how would you choose this P then? Well, you can actually show the following for any Q. Now you fix Q here. You just fix Q. Say Q is 1001. Okay, so this is positive definite, obviously. So you choose this Q like this. Okay, and then you just solve this. You just solve this Lyapunov equality. Then you will get P. And you can show that this P is always positive, definite. Okay, how would you show that? Okay, so you set P to this way. Okay, so this is in fact the solution to Lyapunov equation, P plus PA minus Q. Okay, you choose whatever positive definite matrix Q, then the solution to this Lyapunov equation turns out to be this. And P involves this integral of matrix exponential. Okay, so Q is positive definite, and now you have matrix exponential on the right, and also the transpose of matrix exponential on the left. Okay, and you can show that this is positive definite. This is positive definite. Okay, definite. And why is the solution of this Lyapunov equality? Well, you can directly plug in this P here and here to check this is true. Okay. Well, A transpose here and the P is integral, so that's why you have integral, and E to the A transpose T Q E A T, and now P comes first, and so you have put this P here and then A. Okay, and you can check that this is the differentiation of this one with respect to t. It means you differentiate this one first and then differentiate this one. If you differentiate this one, then it's going to be A transpose and the whole expression here plus. Now if we differentiate this one with respect to t, then this a can go outside here, and then you just write down this expression. Okay. Okay. So then you have 0 infinity and d by dt. Okay. E a transpose t q e a t. Okay. dt. Right. And so this expression is differentiated and integrated. And so if we do this operation, then this original expression comes out, q e a t, and you have to evaluate this one at infinity and 0. If we plug in t equal to infinity, and the whole expression will be 0 if a is stable. Okay? If a is stable, if all the eigenvalues are in LHP, you can show that, I mean, this guy would be 0 when t is infinity. Okay, that can be easily shown actually. And so the 0 minus, you plug in t equal to 0 here, then this part will be 1 and this part is 1, or identity is going to be q. Okay, so this expression is in fact minus q, and we just show that this p is the solution to this Lyapunov equality. Okay, as I said, you can show that this p is positive definite. And so, I mean, this clearly tells you how to choose this p, the p here, how to choose this p to check the internal stability of linear system. Okay, so if you choose p this way, then it doesn't work. Okay, so not every p will work, but if you choose your p based on this formula here, then you will always check the correct stability for a linear system.